Dear professors and colleagues, my name is Shixiang Zhao. I'm currently working at St. Petersburg State University with Professor Petrov Yuri. And today it is my big pleasure to share our research work on the topic about the constitutive modeling for some metallic materials and impact loading across a wide temperature range. In the first part of my presentation, I would introduce some existing phonological models of the plasticity, including the model that we are developing, which is the relaxation model of plasticity. So at the beginning, in this area, as you know, there is a large number of different phonological models for capturing the coupled rate temperature effects. For instance, we have the Johnson-Cook model. I hope you can see what I'm pointing out. Yes. We have Johnson-Cook model, Huang-Liang model, and numerous there were no modifications shown here. And these models, they commonly use this kind of multiplicative form to account for the hardening effects, the rate sensitivity, and thermal softening behavior for under different loading conditions. And nowadays they are widely used in practice due to the simplicity and also the ease of implementation within the finite element frameworks. So they also typically assumed by introducing these empirical components, which depends on the strain rate and temperatures, into this well-known classical existing basis, which was initially developed for the quasi-static case. And furthermore, many other models are proposed based on this general multiplicative form shown in expression 2, where you can find two different multipliers here, depends on the strain rate and temperature separately, which is also aligns with the temperature rate correspondence, which states that the stress obtained by increasing the strain rate can also be achieved by lowering this temperature. So this is the empirical feeding approach to study the coupled rate temperature effects. Well, in our laboratory, we are developing the incubation time approach proposed by Professor Petrov. In this approach, the rate sensitivity of materials is regarded as a manifestation of their time sensitivity. For instance, in this dynamic integral yield criterion 3 proposed by Professor Petrov, we have the function sigma big here, which represents the stress level at elastic stage. And this sigma y is a quasi-static yield strength, it's a material constant. And also we have two different parameters of the criterion, where here this parameter tau is called the incubation time parameter, or in this case, it is also regarded as the characteristic relaxation time parameter. And then just by introducing this functional in expression 4, which actually represents a certain mean stress in a time space, and can also be regarded as a dynamic stress intensity. So using this functional introduced here in expression 4, we can reformulate this inequality 3 to derive the yield criterion shown in the equivalent form 5. And this new dynamic yield criterion states that the yield begins when this stress intensity reaches a certain critical value, which is a material constant sigma y. And you can also find in the figure 1 the redependence of the yield strengths for this aluminum alloy. It shows that the yield criterion 5 provides a better agreement with the experimental data, comparing with this performance used in the Johnson-Cook model, represented by this right line. Later, we proposed the relaxation model of plasticity based on that integral yield criterion. So in this context, we have the equation 6, which calculate this true stress, and also have expression 7 determining this function gamma, which is the relaxation function. And most importantly, it involves this function M alpha, which includes the relaxation time parameter tau. So finally, we can derive the RP model, the relaxation model of plasticity, in the form 8, where again we have two multipliers. The first one is rate independent, and it is supposed to describe the stress responses of materials under quasi-static loading conditions. And the second multiplier here, which contains this relaxation time parameter, is responsible for the rate sensitivity of materials. And for the choice of the first function sigma c, you can there are many other options, not just shown in this slide. And in the case of constant strain rate, which we already have under experimental conditions, then we can analytically calculate this function of alpha and derive the RP model in the rate-dependent form as shown in expression 11. And this demonstrates the fact that the rate sensitivity of materials can be regarded as a manifestation of their time sensitivity. And finally, just by introducing this dimensional rate-dependent variable chi, we can derive RP model in the final form shown in equation 12, where again sigma c accounts for the stress ring diagrams of materials under quasi-static loading conditions, and function g is rate-dependent function. It is responsible for the rate sensitivity of materials, and it can also be proved mathematically that this function g possesses at least three different properties, showing its ability to describe the rate sensitivity, ability to incorporate the temperature time correspondence, which will be discussed later, and also to ensure the uniqueness of parameter values used in the model 12. So generally speaking, differing from other phenological models mentioned before, one of the main advantages of the RP model is its ability to describe these non-monotonic stress ring responses of materials under various loading conditions. For instance, in these ultrafine-grained materials, particularly in these different magnesium alloys, the phenomenon known as U drop, as shown here, is often observed. So it means a sudden drop in the yield stress when we reaches the yield limit. I mean, once after the onset of the yielding process. So figure 2 shows the ability of the RP model to accurately capture this non-monotonic behavior, because RP model recognize this phenomena as a relaxation process. And this slide explains why, in our opinion, this general multiplicative form 14 are unfortunately unsuitable for describing the stress responses of materials, especially across a wide range of both temperatures and strain rates. Because if we just look at this relative stress factor shown here, which is a ratio of the true stress at high strain rate to the ratio a ratio of the true stress at high strain rate to the stress level at the quasi-static strain rate. Then, oh yes, it is also shown here. Then this general multiplicative form 14 will provide such relative stress factor, which is actually independent of temperature, because during this division, the last multiplier just cancels out. So you can find the example shown in expression 15 of what we get based on the Johnson-Cook model. It is temperature independent. However, the experiments, for instance, for this high-strength low-alloy steel 65, show a very clear this temperature dependence of the relative stress factor, as shown on the right side of this figure 3. So this already indicates a limited performance of this general multiplicative form when we use it in a case where we have to work with a wide range of both temperatures and strain rates. Furthermore, it also implies the existence of the temperature time correspondence. So we have temperature rate correspondence, which states that the stress obtained by increasing the strain rate can also be achieved by lowering the temperature. And models following this general correspondence usually provide a temperature-independent relative stress factor shown here. And it is an empirical approach to study the rate sensitivity of materials. Well, in our laboratory, we're investigating the temperature time correspondence, which actually gives the temperature dependence of the relaxation time. I mean, the relaxation time parameter tau. First of all, in our opinion, it is reasonable to do that because the relaxation behavior should be influenced by temperature. And also, just back to the RP model, although we have a function sigma c here, which already depends on temperature and contributes to the thermal softening behavior, but still it is necessary to introduce this temperature time correspondence due to that experimentally observed temperature dependence of the relative stress factor. Because in the RP model, this relative stress factor is determined by the function g, which is also equal to the second multiplier of the model. Therefore, this functional M alpha and thereby the relaxation time parameter shall be temperature dependent. And this indicates the existence of the temperature time correspondence. Furthermore, as temperature increases, the value of the relative stress factor and thereby the value of the function g decreases for many materials. And that leads to a decrease in the relaxation time parameter, because we can mathematically prove the monotonicity of the function g with respect to the relaxation time parameter. And this already indicates the qualitative changes in the relaxation time parameter as a function of temperature. Here's one of examples in figure 6 about the stress strain diagrams of this high-strength steel at different temperatures and strain rates, along with corresponding simulation results used from different models shown here. And these different colors correspond to different temperature conditions. And one of the key points here is the ability of the RP model to capture this negative hardening behavior occurred at low temperature and high strain rates. So this is caused by the rapid adiabatic dissipation. Because as we know, under impact loads, the plastic deformation process is adiabatic because the loading rate exceeds the rate of heat exchange. And as a result, the heat generated by the plastic deformation, they cannot escape from materials, but remain trapped inside material, rising its temperature during the deformation process, rising its temperature, and therefore leading to this reducing this stress level. So this is a typical stress relaxation process and a very special thermal softening behavior of materials under impact loads. Although you can find the hardening behavior in other loading conditions. So this special adiabatic nature of materials can be described by the equation 16, where this coefficient, which named as the Euler Queening coefficient, plays a very important role here, because this coefficient determines the fraction of this deformation energy converted into the heat energy. And in this case, the value of this coefficient was determined by Professor Nebenetzer in experiments. However, using the same equation 16, other models only provides a weak tendency towards this softening behavior, whereas the RP model can quantitatively capture this non-monotonic behavior. One of the reasons is the introduced temperature time correspondence, because during this deformation process, the temperature rise further reduces the relaxation time value. That leads to a more pronounced stress relaxation, which means the softening behavior. In the last part of my presentation, I'll do it more quickly. The finite element simulation using the RP model is represented. So generally speaking, in the finite element analysis, we solve this dynamic equation by this explicit central difference method. And we also use the return mapping algorithm combined with the implicit Euler method to treat with these differential constitutive equations, where the RP model is used here to establish this U-surface equation. And for the validation, we conducted a series of numerical simulations. At first, of this Hopkinson pressure bar experiments. In this test, we can generate a stress wave by impacting the first bar, which is the incident bar here, and then to measure its propagation through the sample itself. And in the second bar, which is the transmitted bar, to evaluate the plastic response of the sample. At the end, we compare the simulation results with experimentally measured stress waves propagated in these two different bars, and also the stress level we can measure of the sample. So here's one of the examples for the titanium alloy. Figure 5 shows stress strain diagrams for these materials at different temperature and strain rates. it shows the behavior of the one-dimensional RP model. Well, figure 6 already demonstrate both the simulated and experimentally measured stressing diagrams of the sample in two different loading cases, as well as the corresponding stress waves measured and simulated in two different bars, in the incident and transmitted bars. We also conducted a final element simulation of the Taylor impact test, where this short cylindrical samples flies at a very high speed in different speeds and strikes the rigid body. And at the end, we compared the simulation results with these experimentally measured geometry characteristics of the sample after impacts here. And all comparison data is shown in the table 1. We can find quite similar numbers between experiments and simulations. And this is a more visible example comparison of the simulation and experimental measurements shown here in the figure 7, two different cases. So they all demonstrate a well performance of the RP model and our computational program. That already led us to the conclusion of my presentation. So first of all, the relaxation model of plasticity, it is derived from the incubation time approach using the relaxation time parameter instead of being introduced empirically. And also in our approach, the rate sensitivity of materials is regarded as a manifestation of their time sensitivity. And also RP model is able to capture different non-monotonic stress and behavior responses, including the U-drop phenomena and special thermosolving behavior under impact loading. And also we developed the numerical program suitable for performing the numerical simulation using the RP model. Yeah, that's all. Thank you for your attention.